The purpose of this presentation is going to be vegetation identification and filtering in SfM-derived point clouds of high relief coasts. So it's similar to the challenge you might see here, where we have a high relief coast, we have vegetation overhanging it. How do we distinguish the vegetation change from the geomorphic change? So that's really going to be the focus of this. It's not a localized or isolated issue. This is presents a global challenge in order to predict cliff and bluff erosion at multiple spatial and temporal scales. We really need this high resolution information in order to improve our understanding of the processes that drive these change in these dynamic environments. So we can see it's in New Zealand, it's in the Great Lakes, it's all throughout the US and global challenge. And really, this is more so driven by development on cliffs and bluffs tends to continue to pick up and to continue to accelerate despite the climatic variability and uncertainty in the future. So the challenge here really is we have increased development pressure, but we have really a paucity of data or a lack of data in these environments despite how dynamic and how rapidly they can change. There's a couple of different tools that are useful for coastal monitoring of cliffs and bluffs. One is a terrestrial laser or LiDAR survey, where you have a laser system or a LiDAR system set up on the beach. These can provide really valuable information, but as you can see here in the upper image, there may be missing data depending on how that survey is set up and potential shadow issues. Another option that's frequently applied is aerial LiDAR surveys, like what you see on the bottom here. The challenge that you notice with this, or you may see with this, is that there's very large data gaps, which may be due to data processing, post-processing, and data availability. So really, how do we address these data gaps and really get a more comprehensive picture of what the cliff or bluff looks like? So we could do this through SfM, that is structure from motion. So where we have a series of photos taken while walking along or traveling in a boat or other vessel along the coast, we can get a series of photos looking at the bluff, and by matching pixels across multiple photos, we can develop a 3D, really dense, high-resolution point cloud. And this overcomes one of the traditional challenges with LiDAR, which is, as you see on the right here, let's say we have a LiDAR beam is traveling down, and depending on how that data is processed or post-processed, we may actually miss the bluff face completely. This is also even more important if you think about potentially overhanging areas of cliffs or bluffs. So really, SfM provides us an opportunity to develop really high resolution and high accuracy products of these near vertical or vertical facies, which we can then use for change detection analyses, as you see here, where a point cloud from November 2016, only a couple months later in January 2017, we see that there's been one large failure and one more minor failure that are picked up in the change maps just by simply subtracting these point clouds. So SfM in these vertical surfaces of these high resolution, high relief environments is going to be important going forward. So for the case study here, to look at how do we segment out this vegetation from the geomorphic cliff itself, we're really going to focus on a case study of the Elwha Bluffs. This is a section, it's a 1.5 kilometer long section just east of the Elwha River Delta. And the driving force behind the initial collection of these photos was the large dam removals from the Elwha River, and so that restored connectivity between the ocean and the ocean and the river itself, and really resulted in a large distribution, a large flux of sediment towards the coast and potential building of the beach. So these photos were initially collected to try to evaluate how the bluffs may have changed in reaction to these dam removals. So there's a couple different approaches you can use to process your photos into a 3D dense point cloud. You can use a 3D alignment, 4D, or fixed floating. The 3D is the most common one used, where you have photos from one date that are aligned only with that date being processed. For purposes of going forward with this presentation and this project, we're going to focus on a point cloud derived using a 4D alignment because it tends to have more accurate results with less residuals and fewer outliers. If you want more information about this, there's a forthcoming publication in the special issue of Continental Shelf Research. So the real challenges here, or the kind of the goals, are really to quantify geomorphic change even when this vegetation is present, which can be a real challenge because vegetation is going to change throughout a growing season. If we're trying to figure out what areas of the cliff may have micro erosions, that becomes a real challenge when we have vegetation present and we're trying to do it in a more automated sense. And then with that, how do we efficiently and accurately segment these point clouds into vegetation and bare earth point clouds, just to kind of simplify it and just kind of lump all vegetation together and all bare earth point clouds, all bare earth points together. However, as I'll mention at the end, that's not necessarily the end all be all. There's other options beyond that. But we're going to focus on primarily vegetation versus no vegetation or versus bare earth. So if we look at one possible approach to do this is actually really derived from imagery analysis, photogrammetry, and that's using vegetation indices. So we take the red, green, blue value of the photo and we combine them using a couple of different approaches, any number of different mathematical approaches, to really get a vegetation index, which is what we see on the right here. And you can threshold that using manual thresholding or Atsu's method or any number of approaches. The important thing is it can help you distinguish vegetation from bare earth points. The challenge with this is that we see that there's any number of vegetation indices that you could use. The challenge is which one is most appropriate. You can see some like excess blue really pick up the more brown vegetation, whereas others like excess green and excess green minus red may pick up more of the live vegetation. And then the modified red-green vegetation index on the upper right there actually does pick out the brown vegetation fairly well, but it has some challenges. So if we're using a vegetation approach, which one do we use? And I would argue that we actually need to get away from utilizing the raw images themselves and start to work with point clouds, which allows us to also go back further in time where we may not have the raw photos, but we have a point cloud that's been colorized with RGB values. And so in this case, we're assuming that we don't have a near infrared or red edge or any other hyperspectral band available. You can do this from point clouds in Cloud Compare already. You can do it in Metashape. You can also use these different vegetation indices only adapted to a point-by-point basis. You can also use a machine learning approach. So the idea is, regardless of whichever approach you do, you take the image on the point cloud on the upper right here, and we're trying to segment out vegetation from bare earth points. So in all the following graphics, wherever you see kind of wherever you see brown and green points or areas of the image, the green is going to be classified as vegetation and the brown is going to be classified as bare earth. So using Cloud Compare is not the most efficient approach, however it is possible, and you can see an example here where we've taken and we've classified the above point cloud using the Cloud Compare classifier, and to do this we provided 2 sample or training point clouds, and each of those had only vegetation or only bare earth point clouds. And so this approach does work. It provides about an 88–89% accuracy, which is not bad. However, you can see in the areas here highlighted by the bounding boxes that there tends to be a lot of speckling of false points that are classified incorrectly as vegetation on the bluff face, which are actually bare earth points. And it's important to note that even some samples from this point cloud were used in the classification input, the training data sets. So trying to figure out a more objective approach to this, something that maybe is a little more accurate, a little bit more efficient, we're exploring the use of machine learning for this. And machine learning is kind of a catch-all term, so there's any number of different inputs that you can feed into any given model. You can feed in the red, green, blue values themselves, or one or more vegetation indices. You can feed in the raw geographic coordinates, so the XYZ coordinates, or even any number of derived morphometrics such as slope, standard deviation, etc. And then the other challenge is, what model architecture do we use? What's the training validation split? What are the number of layers? How many nodes per layer? What exact API we're using has a influence on how complex we can make the model. And then what activation functions and dropout are we using? So for purposes of this model, of this research going forward, we're using an activation function of rectified linear units. We're using the functional API, and you're going to see that we're going to vary the number of layers and nodes, but we're using a 70-30% training validation split and a dropout of 0.2. And those are all to kind of reduce the likelihood of overfitting and trying to make the model more robust in terms of its application. So looking at some of the results, we see this is using just the red, green, blue values, and it's using 3 layers. So what you see is 16, 16, 16. That means there's 3 layers. Each of them has 16 nodes per layer. And what we see here is we have about 625 trainable parameters, a pretty good training time, only just over 8.5 minutes. And the accuracy compared to the cloud compare goes from 88, almost 89%, up to 93, almost 94% with this. So it actually does a pretty good job with a relatively simple model. But how does this work when we add any number of vegetation indices in addition to those RGB values? Well, when we add the vegetation indices, what we see is almost a doubling in the training time with a very, very minor bump in accuracy. So we take much longer to train. We only have a few more trainable parameters, but the accuracy goes up very, very minimal compared to the RGB only 3-layer model. How does this work when we vary our number of nodes and our number of layers? So we also tested using just RGB values and a more complex model, that is more layers and more nodes per layer. And what we see is the trainable parameters in just RGB. It's a 6-layer model. The training time is similar to the RGB, the simpler model, and it's a almost equivalent training, or almost a comparable accuracy to the very, very simple model. So really took almost 2 minutes longer, but a comparable accuracy, suggesting that the simpler model may be more appropriate. Similarly, when we add in all the different vegetation indices that we computed here, which is about 12 of them, the trainable parameters was a little higher, but the training time almost doubled. And again, a very minor bump in accuracy. So we didn't even run the prediction time on this because it took so long to train. All this is to suggest that there's a very, very minimal improvement in accuracy compared to how much more time it takes to train that model and how many more tunable parameters there are. So this all suggests that maybe a simpler model is more parsimonious and more appropriate for vegetation segmentation in these high relief environments, and that using red, green, blue values only compared to including any number of vegetation indices, we actually get a better performance relative to the training time and the number of parameters, tunable parameters, using that RGB only model. So in this case, it's kind of nice that the simpler model works out better. Future challenges or opportunities we're working on further democratizing data collection, so empowering coastal communities and stakeholders to actively engage in ongoing cliff and bluff research at a variety of different spatial and temporal scales. Really getting these people who are in the environment, who have a vested interest in it, is going to be important going forward and trying to help address some of these data gaps. And this is the focus of a forthcoming publication in Continental Shelf Research listed here. Keep an eye out for it. And then regarding vegetation segmentation or filtering using machine learning, more parsimonious models. So a simpler model tends to actually outperform a more complex model relative to how much training time it takes. So these models are more efficient to train and predict even than the cloud compare alternatives or Metashape alternatives. And there's also the potential to expand the current classification approach to include multiple classes. So beyond simply vegetation bare earth, we might include woody vegetation or deciduous versus coniferous or any number of classes. And that would have to be further explored. So here's the references, and thank you for listening to the presentation.